Well, good afternoon. I wish I'd had a beer. I had a cup of coffee instead, so I'm thirsty and irritable. But one thing I'd like you to notice on this picture, the big guy moves off to the right, and what I want you to focus on is the guys to the left. And you'll see this kind of scenario again. And I wanted to sort of reiterate some of the concepts that Lindy had in her talk and kind of flash through them. When I was a kid, we learned, these kinds of things, that you melt down a planet and you make the meteorites. If the planet's not too big, you can leave some different kinds of meteorites at different levels. And you get these kinds of pictures. This is from an early textbook where you have this core formation inside of a planet and formation of rock and mantle. And I really like, this part, then it explodes. And I always thought that was so cool, right? The planet's going to just explode and out comes the iron cores flying out there. And, and getting into grad school, you never know what's, people really know and what they don't know. And so this was one of those things like, wow, they really do that? And how do you get the iron from the very centers of these planets? And then we have this revolution in our dynamical understanding of planet formation, where you have the planetesimals or embryos. Everybody spends 2 hours trying to say what's a planetesimal and what's an embryo. But planetesimals usually things too small for you to resolve with your code, just so you... And the embryos are things big enough to actually resolve. And then you get planets. And this is a very useful kind of model because you can see that water gets delivered to the inner solar system from the outer solar system. And there's some problems. You have very high eccentricities of the final terrestrial planets in most of these models. And a lot of this may be because perfect sticking is assumed. And what that implies for dynamics is one thing, and I won't get into that, but what it implies for composition is another. And so you can start with these chondritic objects, and you form a chondritic planet. Like the Earth is presumably bulk chondritic, and Mars is presumably, kind of bulk chondritic. And you don't have any kind of pathway to deviate from this bulk composition if everything you do is happening with perfect accretion. And so it limits how you can explain them cosmochemically. And Guy Collinsomagno has a very controversial talk and paper that just came out about Vesta in this regard. So there you have these final planets, and the question is, how are they so incredibly diverse when you've done all this stuff? You have Mercury, which is mostly iron, it's like 70% iron. The Moon, which is at most, a few percent iron. And then you have Mars and Earth and Venus. And Earth and Venus are always, we're taught that they're twins, and they do seem to have comparable compositions. And it seems like the uniqueness, the diversity seems to increase the smaller you get. And the focus of the talk is that pairwise accretion, this process we think of, is really quite messy, and it doesn't usually work out. In fact, here's a typical event. This would be a typical velocity, like 2.5 times the mutual escape velocities of the bodies. If you look at the plots by like David O'Brien and people looking at n-body simulations since then, what are the average encounter speeds of two planetesimals or embryos colliding? And it's a couple of times v-escape. This scenario is kind of a scale similar, actually. And then when you get crank things quite a bit slower, now you're at 1.4 times v-escape, these bodies have a chance to accrete. And I'm going to show that simulation a little bit later. But what's kind of interesting is you have this draping back of collisional material, processing over the period of a couple of days, going back onto the top of the object. So that sort of sets the background that you have this pairwise accretion is actually quite inefficient. Only at the very lowest velocities do you have efficient accretion. And when you get out here to the kind of velocities people see in dynamical simulations of planet coagulation, you have kind of a 50-50 chance of either partially accreting or having what are called hit-and-run collisions, which was the first simulation I showed you. So a little vignette that I was advised to remove from the talk because I'm going to run out of time. But the chondral formation timescale and the core formation timescales of planetesimals are comparable. One might say coeval. There's a lot of uncertainty on these data. But this first 1 to 3 million years, it's interesting for 3 reasons. One, things seem to have been big enough to be melting down all over the place. That's kind of the core formation timescales that people are measuring for the earliest cores. Chondrals are forming. Those are kind of the ages for chondral formation timescales. And that's the dynamic timescale of the onset of embryo-embryo accretion. And so we came up with this idea a few years ago that this might have something to do with the formation of chondrals, namely that you have accretion going on. The accretion is very imperfect, so don't worry about this big guy. It's just going to sit there for the most part. This one's going to get ripped into a, well, actually in this case it's slow enough. This is actually V escape equals V impact, so it just kind of falls onto this guy. But pieces of it go flying off at become depressurized. They start at about 10 bars of pressure, and they end up within a few hours at 0 pressure. And so we constructed this model where you can form droplets in these plumes. And then when I started hearing about this, magnetic fields being detected in Allende and other chondrites, it seemed to make sense to me because if you make chondrites around an object that has a core, and that core is starting to become responsible for a stable dynamo that might be imprinted, maybe this is a self-consistent story. And so this chondral lid, or the crust that Lindy was talking about, may be, instead of being primordial, maybe it gets draped on top, and it's a chondral processing factory. Now, I guess I should show you. That's kind of the same simulation. So you get this merger, rotation of the core, possible instigation of a dynamo, and draping back of these chondral forming materials. That's the whole problem with the theory, though, is that if you differentiate and have efficient core formation, then you no longer have the primitive materials from which you wanted to make the chondrals, right? So it's a conundrum, and I don't really say that we have the answer. But it's the nuances of differentiation of 10 to 50 to 100 kilometer diameter bodies are not understood. And I think that's the take-home message from the previous two talks, is that there's a lot of uncertainty in how cores form in these smaller bodies. So I'm just going to leave this kind of as a whether you can really form chondrals by accretion, even though I think that it works out in terms of mass balance and timing, possibly composition. And there's a lot of things going on to stir up these convective zones inside of the settling materials during this time. But I'll fast forward to a bigger problem. So that's the tiny end now. The big end is Mercury, which is an embarrassment among the planets because it's got no mantle. And we have to find out where that mantle went, right? It didn't go into the sun. It didn't go, or maybe it did. The classic Mercury formation giant impact model by Benz et al. Has a giant impact hitting Mercury, and dynamical modeling shows that should drape back onto the planet pretty quickly before it disperses. And so this will be a very simple conclusion here because it's a simple concept that you have sort of a heads and tails scenario, 50-50 chance of accreting or bouncing, basically. And if you pick a planetary embryo at random, and now assume you're not going to model the dynamics, and this is stuff that's been done by John Chambers in 2013. This is starting to have the capability to track dynamics, including fragmentation and hit-and-run collisions, and they're consistent with the statistical model. But you have like a 50-50 chance of accretion, and every time you accrete, you drop the coin into the jar. You've accreted it onto the bigger planet. And every time you don't accrete, you leave it on the table and give it a mark. And by the end, you have a bunch of coins on the table. Many of them have marks on them numerous times. In fact, the more attrition there is, the weirder and more bizarre the final objects are. And so you can plot this for 20 objects accreting until you have 2 leftovers. The jar is full. That's Venus and the Earth. And the 2 leftovers are sitting there on the table. This black dots is the fraction of the surviving population that has had this number of hit-and-run collisions and has not been accreted. And so you divide that kind of in half. Half of them are to the left of the peak, half to the right of the peak, more or less. And so you'd expect one Mercury-like planet and one Mars-like planet. By Mars-like, I mean a planet that was largely left alone by luck, and then one planet that got picked on twice, or once or twice or more, but didn't get accreted. And so Mercury is like this planet that got picked on. And so we model this, a single hit-and-run collision. You can indeed make Mercury. And here's the target starts off here. The target ends up there. It's about the same. It could be proto-Venus. It could be proto-Earth, depending on the dynamical scenario. And then off goes this object, which has about the mass of Mercury. And so we're trying to match this, match Mercury. And this is this field of outcomes. where you have a lot of objects. You lose about half their mantles. It's easier to remove half the mantle than to remove 70% of the mantle, which was required for Mercury. So you could have multiple hit-and-run collisions or a single hit-and-run collision. These are ways to make Mercury. It's the same lost mantle question that we were addressing with, where's all the basaltic BBs if you didn't have chondral formation and you had basaltic BB formation by this process? Where is all the basalt? Where's all the remnant from these iron cores? And the solution in this scenario is that the mantle ends up going onto the planet that it hit, because they're both orbiting the sun together. They're likely actually to accrete. Most likely they're going to all accrete, and most likely everything's going to end up inside of Venus and the Earth. But most likely isn't everything. Mars, Mercury are about 1/10 of the planet-forming mass in the terrestrial planet region. And so you dispose of the material by accreting it onto the bigger objects. Where's the mantle of Mercury? It's on Venus or on the Earth. And so this attrition bias of the survivors continues to increase until finally you've got a few left. And depending on the magnitude of the attrition, for instance, planetesimal formation, let's say you start with 100,000 and end up with 3,000 parent bodies of the asteroids. I just kind of made those numbers up, but it's not too far off. Then you can get Vesta-like objects on one side of the hump and Psyche-like objects on the other. And you can get a lot of freaky objects that might have had 4, 5, 6, 7 hit-and-run collisions in a row, removing virtually all their mantle, which I think is a viable model for Psyche. So I'll just leave my conclusions up there and take questions.
Thank you very much. Other questions? Yes.
Eric, it sort of sounds like then you can explain Mercury more easily than Mars. Is it like a lower probability that Mars didn't get any runs? Does that become a bigger problem?
Not really. You end up with a distribution like that. And so Mars would be something that got 0. So this would be 0. 10% of the population, of the surviving population would have 0. 30% or so would have 1. A lot of it goes back on. It's a pretty simple model. And then, of course, we think Mars might have had very unique dynamical circumstances. So it's not really a fatal problem. You would expect one of them to be, that would be the coin that you never flipped. You never got around to flipping it.
Are there other questions? Yes, in the back.
Are the Mars-like and Mercury-like populations spatially distributed in such a way that they could end up forming a planet? This is just a histogram.
Yeah, this is just a histogram. If you look at John Chambers' 2013, he ends up with a planet out by the orbit of Mars, actually, that has had 2 hit-and-run collisions in a row. He truncates the inner solar system at 0.2 AU in his calculations. So you wonder if that's going to bias where Mercury ends up forming.
One more question, perhaps? Well, if not, thanks again, Eric.